Welcome to the Macalloy presentation on corrosion protection. Hi, I'm Matt and I'm one of the engineers at Macalloy. And I've been at Macalloy now for just over 2 years.
Hello, my name's Mark and I'm one of the area sales managers at Macalloy. No, I'm not Matt's younger brother. I've actually been at Macalloy for 25 years, which is longer than Matt's been alive. We just thought we'd give you a brief introduction and insight into some of our favourite projects and products.
So what we aim to do is give you an idea of the coatings and protective systems we offer at Macalloy and hopefully provide you with a better core understanding of these systems and how these are used. So on the left hand side you can see some of the topics we're going to cover, and on the right hand side you can see some of the system applications. So you'll notice that we've numbered each slide in the bottom right hand corner. So if you do have any questions, please do make a note of the slide number, and what we'll do is we'll revisit those points at the end. So we'll start off with corrosion. Corrosion is a natural process that converts and refines metal into a more chemically stable form, such as oxide, hydroxide or sulfide. Metal corrodes when it reacts with another substance such as oxygen, hydrogen, an electrical current or even dirt and bacteria. The images show a pin used in a swimming pool environment bolting two adjoining truss sections. A 316 stainless steel pin was used, however, as you can see, severe corrosion occurred. The paint was not applied correctly to the carbon truss, and as a result, bimetallic corrosion transpired. As a result of poor maintenance, moisture was able to pool within the slot of the truss, thus leading to crevice corrosion. Macalloy were asked to survey the structure and assist in supplying replacements in duplex.
Common types of corrosion. Uniform corrosion. This is the most common form of corrosion, which usually takes place evenly over large areas of a material's surface. Pitting corrosion. This is one of the most aggressive forms of corrosion, and pitting can be hard to predict, detect or characterize. This localized type of corrosion happens when a local anodic or cathodic point forms a corrosion cell with the surrounding surface. This pitting can create a hole or cavity which typically penetrates the material in a vertical direction down from the surface. Pitting corrosion can be caused by damage or a break in the oxide film or protective coating, and can also be caused through non-uniformities in the structure of the metal. This dangerous form of corrosion can cause a structure to fail despite a relatively low loss of metal. Crevice corrosion. This form of corrosion occurs in areas where oxygen is restricted, such as underneath washers or bulkheads. This localized corrosion usually results from a difference in the ion concentration between two areas of metal. This stagnant microenvironment prevents circulation of oxygen, which stops repassivation and causes a buildup of stagnant solution, moving the pH balance away from neutral. This imbalance between the crevice and the rest of the material contributes to the high rates of corrosion. Crevice corrosion can take place at lower temperatures than pitting corrosion, but can be minimized by proper joint design. Galvanic corrosion. This form of corrosion occurs when two different metals with physical or electrical contact are immersed in a common electrolyte, such as salt water, or when a metal is exposed to different concentrations of electrolyte. Where two metals are immersed together, known as galvanic couple, the more active metal, the anode, corrodes faster than the more noble metal, the cathode. The galvanic series determines which metals corrode faster, which is useful when using a sacrificial anode to protect a structure from corrosion. Intergranular corrosion. This corrosion occurs when impurities are present at the grain boundaries which form during solidification of an alloy. It can be caused by the enrichment or depletion of an alloying element at the grain boundaries. This type of corrosion occurs along or adjacent to the grains, affecting the mechanical properties of the metal despite the bulk of the material being unaffected. However, this is generally only an issue in structural applications where welded components are used. Stress corrosion cracking. This refers to the growth of cracks due to a corrosive environment, which can lead to the failure of ductile metals when subjected to tensile stress, particularly at high temperatures. This type of corrosion is more common among alloys than with pure metals, and is dependent on the specific chemical environment, whereby only small concentrations of active chemicals are required for catastrophic cracking. Now let's look at corrosion categories. For the purposes of ISO 12944-2 Atmospheric environments are classified into 6 atmospheric corrosion categories. These range from category C1, which is very low, to category C5M, which is very high. C1 categories are outlined as interior-only environments, such as shops, offices, schools, and hotels. The C3 medium category outlines urban and industrial atmospheres with moderate sulfur dioxide pollution or coastal areas with low salinity. This includes environments with high humidity and air pollution, and such examples may include food processing plants, laundries, breweries, and dairies. C5M is the highest category and refers to coastal and offshore areas with high salinity. This also includes buildings or environments with almost permanent condensation and high pollution levels. It is also worth noting that some hot and humid coastal areas can experience mass and thickness losses greater than the C5M category. Special measures must be taken when selecting an appropriate coating system in such environments.
Prior to any coating, the steel must be cleaned and prepared. At Macalloy, we generally opt for abrasive blasting. This is done externally in accordance with EN ISO 8501 Part 1, which outlines the 4 categories below. SA1 is a light blast clean, which when viewed without magnification, the surface shall be free from visible oil, grease and dirt, and from poorly adhering mill scale, rust, paint and foreign matter. SA2 is a thorough blast clean, which when viewed without magnification, as with all the others, the surface shall be free from all shown deterrents. Any residual contamination shall be firmly adhering. SA 2.5 is a very thorough blast clean, which when viewed without magnification, the surface shall be free from all shown deterrents. Any remaining traces of contamination shall show only stains in the form of spots or stripes. And SA3 is cleaning to visually clean steel. When viewed without magnification, the surface shall be free from all deterrents. It shall have a uniform metallic colour. Preparing products post-galv follows a slightly different process. When preparing galvanised products for additional coats such as paint, T-wash is considered to be the best pre-treatment process. T-wash or mordant wash is a modified zinc phosphate solution which contains a small amount of copper salts. When applied, a dark grey or black discoloration of zinc will result. An alternative to T-wash would be sweet blasting, however it's uncommon at Macalloy, so we decided not to talk about it. Hot dip galvanizing is defined as coating iron or steel in a layer of zinc at a temperature of around 450 degrees Celsius. And during this process, a metallurgically bonded coating is formed which protects the steel from harsh environments, whether they be external or internal. Now the galvanizing reaction will only occur on a chemically clean surface. In common with most zinc coating processes, the secret to achieving a good quality coating lies in the preparation of the surface. It is essential that this is free from grease, dirt and scale before galvanizing. These contaminants are removed by a variety of processes, but common practice is to degrease first using an alkaline or an acidic solution. The part is then rinsed in cold water to avoid contaminating the rest of the process. The article is then dipped in hydrochloric acid at ambient temperature to remove rust and mill scale. This is known as the pickling process. After further rinsing, the components will then commonly undergo a fluxing procedure. Now this is normally applied by dipping in a flux solution which is usually about 30% zinc ammonium chloride at around 65 to 80 degrees Celsius. Alternatively, some galvanizing plants may operate using a flux blanket on top of the galvanizing bath. The fluxing operation removes the last traces of oxide from the surface and allows the molten zinc to wet the steel. From the photomicrograph shown, you can see a series of zinc-iron alloy layers are formed by a metallurgical reaction between the iron and zinc. You can clearly see the distinct layers of steel and zinc joined together by the fusion zone. This zone is generally thought to be around 40 to 45 microns thick. Post-galvanizing process treatments can include quenching into water or air cooling. Conditions in the galvanizing plant, such as temperature, humidity, and air quality, do not affect the quality of the galvanized coating.
With galvanizing, thickness matters. This slide shows the thickness of zinc provided by the various galvanizing processes. The zinc pickup and colour of a galvanised surface can vary with the steel grade. High silicon steel has a higher zinc coating. Increased zinc coating thickness can be achieved by blasting to SA 2.5, which encourages the metal-zinc fusion zone. Spin galvanizing provides a thinner coating but allows the finish to follow the profile better, which is often a desirable architectural feature.
You can see from the diagram the impact that surface preparation has on the coating thickness. Appropriate surface treatment really helps to maximise the achievement of 140 microns as minimum, whereas on spun galvanised components it's very difficult to achieve the greater thicknesses. Here you can see photos of some of the components available at Macalloy. Components such as spades, forks, pin sets, lock covers, turnbuckles and couplers are all spun galvanised, and as standard these achieve the minimum 55 microns as required. The Macalloy bars on the other hand, these are hot dip galvanised. The bars regularly exceed the 85 microns stated as a minimum. Here are just a few examples of projects where galvanised bars have been used. Painted coating. We're now going to give an example of a 3-coat paint system consisting of a primer, intermediate and top coat. Each coating is specified depending on the system requirement for protection and/or aesthetics. The coating or film thickness, generally specified in microns, is key for safeguarding the base material. The paint specification should be provided to Macalloy to guarantee the right system for the application.
And to keep the end client happy, of course.
Now, paint systems may be identified by maintenance schedules that outline a product's design life, which is important to know so you ensure the coating is fit for purpose. Now, as previously covered, the surface prep is essential for the adhesion quality of the paint. The surface preparation not only cleans the steel, but also introduces a suitable profile to receive the protective coating. The primer is applied directly onto the clean steel surface. The primer must be applied to the material within a certain period of time to reduce the risk of contamination. Its purpose is to wet the surface and provide good adhesion for subsequently applied coats. Now, intermediate coats are applied to build total film thickness of the system. Generally, the thicker the coating, the longer the life. Intermediate coats are specifically designed to enhance the overall protection of the system. And finally, the finish coat or the top coat. This provides the required appearance and the surface resistance for the system. This coat is a first line of defense against the elements such as weather and sunlight, open exposure and condensation. These provide the aesthetic appearance of the product and are really what the client sees.
Here is an example of a RAL chart showing 207 colour variants. There are thought to be in excess of 1800 RAL variants. Paint systems vary and can have different properties including the product chemistry, volume solids, gloss levels, dry time and curing temperatures. The type of paint is generally specified by the requirements of the application and environment. The appropriate system specification should be determined by the client. Product chemistry is the makeup of the paint. This is the base products used. These are sometimes specified as polyurethanes, acrylics, polysiloxane and epoxies, to name a few. The makeup of the chemicals will determine the gloss levels, dry time and curing temperature. For a high quality finish, control measures are taken to control timings and temperatures, and lead time should be given to reflect these requirements. Drying times can range from 1 to 72 hours per coat. It is worth noting that most paint options are available within the UK. However, some brands or paint manufacturers may not be feasible. In this likelihood, suitable and agreed equivalents are offered as an alternative.
And here are a few examples of the painted projects we've supplied over the years.
Teflon is a brand name for Xylan, which is a fluoropolymer-based industrial coating, generally used to reduce friction, improve wear resistance and for non-stick applications. We use Xylan at Macalloy to prevent environmental and bimetallic corrosion. An example of this is for coating stainless steel pin sets that are being used with carbon steel gusset plates. This creates a barrier between the two dissimilar metals, preventing them from reacting with one another.
It is worth noting that the Teflon coating is an alternative to your standard isolation sleeves. This is useful for two reasons. One, so that you don't have to worry about losing the isolation sleeve on site, but two, because you're able to use the same gusset plate dimensions as you would as standard, so you don't have to worry about modifying the plate and hole size.
You may find examples of Teflon within your own home. A lot of cooking equipment is coated in Xylan due to its heat resistance and non-stick properties.
The Xylan coating matrix is composed of three basic ingredients: a polymer binder for film strength, adhesion and protection from the softer lubricating particles, a solid lubricant for low friction, release and resistance to wear, and finally pigments, fillers and reinforcements for colour and additional properties such as hardness. Intumescent paint. Now at Macalloy we get asked about intumescent paint and fire protection quite often, so we thought it'd be quite important to discuss what we know about intumescent paint and to try and share a little bit more information on what we can do for you here at Macalloy. Now, as you may know, structural steel is a non-combustible material which does not contribute to the fire load of the building. However, the strength of the material deteriorates as time passes and heat rises, which therefore threatens the integrity of the construction. Therefore, it's important that a fire protective system is applied to ensure that in the instance of a fire, the building can be safely evacuated. The intumescent coating is basically a paint-like material which is inert at low temperatures, generally under 200 degrees Celsius, but reacts with heat. As the temperature rises during a fire event, the intumescent coating swells and forms a char-like layer that covers the steel. This char layer is of low thermal conductivity, thus acting as an insulating system. It should be noted that the coating usually expands up to 50 times when compared with the original thickness. So for every 1 millimetre of paint applied, the char layer can reach up to 50 millimetres of thickness. So intumescent paints are always made up as part of a system. For steelworks, the system includes an anti-corrosive primer and a top coat. So the primer is used for assuring adhesion to the substrate, anti-corrosion protection and stickability of the intumescent char formed during the fire exposure. While the scope of the top coat is really to provide aesthetic function whilst also adding additional corrosion protection and weathering resistance to the end use conditions. So as you can see from the diagram, number 4 is a structural steel member, so this should be appropriately prepared, as we've discussed before. Number 3 is the primer coat. Number 1 is the intumescent coating, which is normally spray or brush applied. It can also be roller applied. And then number 2 is a top coat, which is obviously to suit the aesthetic finish, which is a bit that you really see last. So DFT is the dry film thickness, and that's quite critical when determining the amount of design resistance you need. So whether that be 30, 60, 90 or 120 minutes, all depends on various factors. So the mass factor, also known as massivity or section factor, is a ratio between the area of the steel exposed to the fire and the volume of the steel section. So the higher the mass factor, the faster the steel will heat up. So this means that the higher the value, the greater the thickness of the fire protective material. So exposure is simply the number of faces that are exposed to the fire. So you can treat both the tension rods and the compression struts exactly the same by just taking the external cylindrical face. So critical temperature is a limiting temperature as a function of the degree of utilisation. So the lower the critical temperature, the faster the steel will reach this. This will result in a greater paint thickness requirement to ensure that the steel section is protected for the duration of the fire. Fire rating is basically the duration of the level of protection required. So in the UK, approved document B outlines minimum requirements for fire resistance depending on which floor and type of building you're relating to. So obviously when you're selecting your fire protective system, it's important to know what test standards and approvals the system has been tested to, as different thicknesses for different systems can offer the same protection, so it's always good to do your research beforehand. So how to choose the best type of intumescent paint for my project? Now that's not an easy question to answer, as the top coat should be specified based upon the intended use of the system and the environmental conditions. The following categories are defined for the fire protective products according to ETAG 018. Type X is the broadest type of coating, and that really covers all conditions, including internal, semi-exposed and exposed environments. Now, Type Y is intended for internal and semi-exposed conditions only. This includes sub-zero temperatures, but not exposure to rain, and limited exposure to UV. Type Z1 is intended for internal conditions only, so that's excluding sub-zero temperatures, and it's generally more for environments with high humidity. And finally, Type Z2 is also for internal conditions excluding sub-zero temperatures, but it's for far more extreme humidity classes that are greater than Z1. So the photos you see are from Independent Tower in Austin, Texas, so you can see that the quality of the intumescent paint is actually really good by comparison to some projects. So they've done a really good job at blending that in and complementing the building fantastically for that bracing structure. Although at Macalloy we cannot advise on the appropriate coating to suit the fire rating required, we can, based on 1993 Part 1-2, advise on which size tension rod would be suitable when left untreated. To determine this, we need to know the following. Which material you need to use. So are you planning to use a carbon or a stainless steel, as that does make quite a significant difference. We'll also need to know the fire load or the load at elevated temperature. And finally, we'll need to know the resistance time. So as previously stated, this could be anything from 15 minutes to 120 minutes. From this, we use the temperatures approximated from the cellulosic building's fire curve in accordance with ISO 834 as shown. With this and guidance from the standard, we can advise you which tension rod would be suitable based on the information you've supplied. And as mentioned previously, under the Building Regulations 2010, approved document B provides guidelines on fire safety on structures within the UK. Specifically, Table B4 outlines the minimum periods of fire resistance based on the building's purpose, height of the building, and even whether a sprinkler system is installed within the structure.
This section covers thermal metal spraying. Thermal metal spraying is a surface coating process that applies molten metal, usually zinc or aluminium, onto the surface of an appropriately prepared material. The two most common modes of application are flame spray and arc spray. Flame spray uses an oxy-fuel flame to melt the wire, and the molten wire material is atomized with compressed air to create a spray, which is then applied onto the relevant surface being sprayed. Anti-corrosion coatings are typically applied with oxypropane systems. Arc spray. This is a process that uses an electric arc to melt the wire. Like the flame spray, the molten metal is atomized with compressed air to create the spray. Both flame and arc are usually manually operated, but can also be applied via an automated process. To achieve a secure bond between the steel and the molten metal coating, blast cleaning to SA2.5 and SA3 prove acceptable for thermally sprayed zinc. Blast cleaning to SA3 standard will, however, provide the best result, especially with flame sprayed aluminium. The life expectancy of the zinc thermal metal spray is approximately 30 years and has been known to regularly exceed this duration. It has been known to exhibit greater than 20 years performance up to first maintenance, even in harsh marine environments. Zinc thermal metal spray can be applied up to approximately 250 microns of thickness. Providing the coating has been applied correctly and without spatter, there is no need for any fettling processes due to the smooth finish that thermal metal spray provides. As the coating is porous, a suitable sealant is recommended. This section covers powder coating. Powder coating is an electrostatically applied powder which is then cured with heat at around 200 degrees centigrade. This provides a very tough and tenacious coating.
The powder is negatively charged and sprayed towards the grounded substrate. The product is then heated and the powder melts into a uniform film. It then cools to form a hard coating. Prior to coating, the steel will require the removal of dirt oxides or welding scale. This is achieved by degreasing, etching and rinsing. However, extra bonding can be achieved by pre-treating with phosphate or chromate. Blast cleaning is also a common surface preparation for this type of coating. Powder coating benefits. It is an environmentally friendly coating and contains no solvents and releases little or no volatile organic compounds.
Very thick coatings can be achieved without runs, provides a smooth and consistent appearance, and the process time for powder coating is very short compared to a similar DFT paint system.
You'll be happy to know that the presentation has finally come to an end, and we'll just quickly recap on some of the available coatings at Macalloy. So as standard, we offer galvanised, powder coated, thermal metal sprayed, painted and Teflon coated products. But as always with Macalloy, we're quite happy to offer non-standard coatings. So if you do have a coating in mind for a project, please do approach us and we'd love to have a look at it for you.
We'd just like to say thank you for your time and interest in this webinar. If you do have any questions or inquiries, please feel free to email them to the email address is actually on the slide, sales@macalloy.com or technical@macalloy.com.
And don't forget to give our page a follow on LinkedIn.